have X in meters again. And I'm going to focus on just the positive side of the bending moment equation or bending moment diagram. Why positive? Any idea? Can anyone tell me why are we focusing on the positive of the bending moment diagram? Anyone? Can you remember why I'm not focusing on the negative? Anyone?
Because it can be determined later during the analysis.
Okay, so the reason why is that is, so when positive bending, what does positive bending? Positive bending means the deformation pattern. Probably 2P you'll learn, but you'll forget. The deformation pattern is smiling face. Okay, when it's negative, bending moment is going to be sad face deformation pattern. Yes or no? How the structure deform elastically. So if you see over here, right, based on how our structure is loaded, our structure is going to deform in this way. Yes or no? Right? That's why we only focus on the positive and not on the negative. Okay. So we know that at 0.5, what will happen, right, is that this is your bending moment diagram. All right. And this will be equal, the maximum bending moment will be equal to 45 kilonewton meter, and this is acquired by 90 times 10 to the power 3 multiplied by 0.5. Okay, right. So but for this course, or for what I'm teaching now, we are only going to focus on here. So later, when you guys are given a beam that has multi-loaded, okay, point distributed load, you have to draw this diagram, and you have to find what is your what? What's your Vmax? Okay, what is your Vmax? That's the important thing, right? So from here, we are going to calculate our shearing stress. Okay, we're going to calculate shearing stress now. Right, so our shearing stress equation is shear xy is equal to shear yx. We're still calculating shear xy shear and shear yx, yes or no, right? So because of the transformation that we have drawn, all right, so over here, because of this transformation we have drawn, we're interested on the shear of this entire surfaces. Okay, but this entire surface will then induce a shear at the top surface. Okay, so like how I explained earlier, that you have, right, we are finding on the vertical face, but in fact it will transmit to the horizontal face. We will transmit to this face over here. Okay, so that's what we are trying to do. So from here, we know that shear xy is equal to shear yx, and then this will be equal, so the shear is in the y direction. So if it's Vy, this will be equal to Izz Qz multiplied by thickness. Okay, so we're going to apply rule number 1. Okay, we're going to apply rule number 1 is that V and I are what? A constant.
Constant.
Yep. So this is rule number what? Rule number 1. Right? So I know that we want to identify what is at point A, what is at point B. Right? I know that. We know that we want to find what is at point A, what is point B. I know that. But okay, we have to apply rule number 1. Rule number 1 states that what? V and I are constant regardless of any points that you are what? Interested. Okay, or not, it get really, really confusing if you don't have all these rules. Okay, so I'm going to like take this diagram now. I need a lot of this diagram. So the next thing that you have to do now, right, is you have to find second moment of area. Okay, so we have this diagram. I'm not going to do it, okay, because I believe you guys are really expert on second moment. So if we look at this orientation now, we know that Vy is going to be from here. Okay, we know that Vy. So the axis of interest, like what I've written earlier, is going to be your what? This line over here. And this is your ZZ. Okay, this is your ZZ. So the first thing we do is we have to find the position of centroid. About or along the y-axis. Right? So we want to find the position of ZZ. And as I said, I'm not going to do it. Right? It's real straightforward, like what we learned in 2 weeks ago. So this will be equal to 35 millimeters from the top. Right? So we realize that the distance from here to here, right? This distance from here to here, this is equal to 35 millimeters. And then the second moment of area, right? So because Vy is in that direction, you are interested in your I what? ZZ. So IZZ will be equal to 5.813 times 10 to the power minus 6 meter to the power 4. Okay, so that's your IZZ. Right. There are two terms that I like to introduce to you guys. Okay. So based on the direction on the shear force, okay, based on the direction, so based on the direction of the shear force, the horizontal member is the flange. Okay. And the vertical member is the web. Okay. So over here, what do I mean by that? So this part is horizontal relative to Vy. This is not known as the flange. And the vertical one, this is known as the web. Okay. It's relative to the direction of the what? Of the shear force. Okay. So now if I were to say what is a flange, what is a web, you'll be able to understand now. Okay. So I'm going to copy the diagram again. Oh, undo. Right. So the next thing that we're going to do now, right? So we know, so we're going to look at the flange section. We're going to derive the first moment of area and the shear stress at the flange. Okay, so let's look at flange section. So the flange section, the limits is 0.1015 meters y, and it will go up to 0.035. Okay, so now why 0.015? So we are aware, right? We are make known that this is the centroid about the y-axis. So this is our location of ZZ. Sorry, I need this diagram to be bigger so you can see better. Right? So this is our ZZ. So we apply to the rule that the analysis, right, will start, or the analysis is at the datum is at the what? The datum is at the centroid on the z-axis, and the distance from here to here now is 0.015 meters, and the outermost is 0.035 meters, right? Because over here, this is 20 minus by 35 is 0.015, okay? Does that make sense? Yes or no? Okay, so we are going to focus on the flange section. So I'm going to sketch out the flange section now. Okay, so this is our flange section. We're not going to consider the web now. Okay, and then we have our centroid ZZ. Okay, so this is our ZZ. So we got our slider now. Our variable y is going to do this now. Okay, so this is our variable y. Okay, so the distance from the what? From the z-axis, from the centroid, we are applying one of our rules, right? The variable y will start from the centroid. Okay, so this is y, right? So this is the area of interest now, right? Why that is the area of interest and not the bottom part? Because why did I tell you? The analysis will start from what? Y max. So this is the analysis direction. Okay. And then we are aware that our next point over here, right? This over here, this is our Y bar. Okay, that is our Y bar that is going to move, that's going to shift relative to Y. Okay, so from here, we can calculate the first moment of area about the z-axis for the flange is equal to A Y bar. Okay, A, so as I said, I like to do width multiplied by depth, and then Y bar. So the width over here, based on geometry, the width over here, what we see is 0.16. Right? And then the depth is equal to 0.035. Okay, 0.035 minus Y. Okay, that's the depth. So this expression over here. Yes.
Isn't the depth supposed to be 0.02, the 20 millimeters, or no?
No, because we are starting our analysis from
Okay.
Y max. Remember, right? We are applying our rule, right? The analysis. So if we look at our rule, right? So the rule says that the analysis will start where Y variable is what?
At max, yeah.
There you go. Okay, and all I'm doing now is I'm applying this formula now.
Okay, thank you.
Okay, thank you. Right. Then the next thing is our Y bar. So our Y bar is equal to 0.5 multiplied by 0.035 plus by Y. Okay, so all this looks familiar, right? It's how we derive it, yes or no? So from here, we have our expression that this is equal to 0.08, and then this is equal to bracket 0.035, okay, 0.0 squared minus by Y squared. So you have an expression for the first moment of area. There is 98 times 10 to the power minus 6, okay, minus by 0.08 Y squared. So this is your equation number 1. Okay. So from here, we can find the shear stress distribution. Okay, we can find the distribution of the shear stress in the flange. Okay, so we now know that shear xy of the flange. So this will be equal